most probably. So today we are going to discuss about the forces between dislocations. Now, forces acting on the dislocation, that is applied shear stress. When it applied to the dislocation, then that exerts a force on dislocation. So we know what is dislocation. Dislocation is a line defect. And what does mean by line defect? It may represent extra half in the particular half of plane, extra line of atom, or missing of a line of atoms. So when such kind of defects is present in the crystalline material, if you put stress, and what is shear stress? Which actually helps to relative movement of between two blocks of a particular crystal. So, or it are also another way of defining dislocation, that it is the boundary line between slip region and unslip region. So both way you can relate that shear stress has a effective and direct impact on the forces of on a dislocation. So applied shear stress going to create a force on a particular dislocation. And motion of dislocation registered by friction. Any motion of dislocation, it actually is registered by the frictional force. And where it is coming? Because the bond strength between the atoms present in the crystalline material. So now we are going to understand what will be the work done by shear stress, and that is equal to the work done by the frictional force. And if you see in the picture there is a dislocation line you are seeing, and F is representing, small f is representing the frictional force, and then these arrow actually tells you the direction of the frictional force, and small arrows are presenting a direction of the shear stress. That you can see the shear stress direction in the upper part of this, and that actually acting or exerting a force on the dislocation. And now our job to understand for that kind of force, shear stress you have applied, and that is the equal to the work done by the frictional force. And so what will be the work done? So that work done of a shear stress, this formula is a B is Barger vector, that is the shear stress, and L1 and L2. L1 and L2 is the dimension of the block, and then you can see that frictional force F into L1 into, and if you equate them, then you can understand the frictional force is equal to tau into B. So shear stress into Barger vector. Now, if you know what is the theoretical shear stress, that is tau max, and when it will be the thing, it will capital G by 2 pi. Now, lattice frictional stress for dislocation motion, tau F equal to that is F by B, and you can represent that G is 2 pi A. You have to remember. Now, lattice frictional stress is much less than the theoretical stress. That we have to understand. What is lattice frictional stress for dislocation motion? It is a source is the interatomic bond strength, and it actually acts to resist the motion of dislocation or movement of the dislocation. So it actually tells you the shear stress by the resistance by the Barger vector. If you then you can see this expression. Now, why lattice frictional stress is much less than the theoretical shear strength? Why is it so? The theoretical shear strength actually representing the perfect crystal, the bond, how they are acting, and how that actually create a scenario when there is an external agency or external forces or external stress is applied, and which can be resolved in a shear component and places that. So it is a perfect crystal. So the bond strength will be very high. They are in the proper arrangement. Already we understand how atomic scale, the bond strength is related to the elastic deformation and plastic deformation. So that concept you can use, and then you understand that frictional stress from the lattice frictional stress, it must be as performances less than theoretical shear strength. And dislocation motion most likely occurs on the closed packed planes where large A interplanar spacing, and in closed packed direction where small Barger vector in plane atomic spacing. That you have to understand. If you want to move a particular thing, suppose you take an example that you want to create some one building, and then you want to dislodge the building, uh, then what you have to do, you have to find the scenario where the certain big gap between the different line of bricks are there. There, if you put force, then you can get the chances of disruption or deformation of that particular. Same way in crystalline material, when two plane are far away, then that plane move through that plane. If you want to move the dislocation, that will be easier, and that must be closed packed plane, because when there is a closed packed plane, then the interplanar spacing are large, and if you go for closed packed direction, then the Barger vector is small, and that actually in plane atomic spacing is less. So that actually the criteria, those criteria are fulfilled plus for closed packed plane and closed packed direction in order to facilitate the dislocation motion. So now onwards you are having a very perfect concept of why dislocation motion occurs at closed packed plane and in a closed packed direction. And if you remember, that is also a criteria for identifying the slip system for particular crystalline material. So slip and dislocation, these correlation actually tells you the dislocation have a very one-to-one relationship with the slip phenomena. So it is the underlying mechanism you can also tell in other words. Now you are going to understand the interaction of the dislocation. Two dislocation may repel or may attract to each other. That two possibilities are there. Either they will repel and they will attract. Okay, depending upon the direction. Now one can ask why they may be neutral to each other. No, because the dislocation always have a direction. So if something is directive, if you take some direction as a positive in a convention, then other direction will be negative. So positive negative will attract, and if you getting same direction for two cases, then both are positive direction, you can tell. So they are going to repulse. So if you see first picture, there the dislocation direction, dislocation Barger vectors same direction. So what will happen? They will repulse each other, and just different. You can see the dislocation. Their direction are totally different, totally opposite. So they are attractive. So this is the way you can understand. Now you have to understand what is the line tension of a dislocation. So atoms near the core of dislocation have higher energy due to distortion. You know that from the last lecture, that when we are discussing the dislocation width, so near the where the distortion are more, when you are near the dislocation core. So here also atoms near the core of dislocation have a higher energy due to distortion, and dislocation line tends to shorten to minimize the energy as if it had a line tension. I mean, you want to minimize the defect, then only you will get the lower energy and stable structure. So dislocation line tends to shorten to minimize the energy. This is very obvious. Now, what is the line tension? What does mean by line tension? It is equal to strain energy per unit length, and it is equal to half of G B square. G is a shear modulus. B is a Barger vector. This is approximately, you should remember that half G B square, that is actually the value of line tension approximately. Now dislocation, how dislocation goes means It looks like a bow, and dislocation can bow due to the force. Dislocation may be pinned by solute, interstitial, and precipitate. Suppose there is in precipitates in the crystalline matrix, or any solute are going to present there, or impurities, interstitials, uh, small size impurities. This substitution levels are sometimes they are not going to pin the dislocation. So dislocation pinning can be done by solutes, interstitials, and precipitates. So pin dislocation can go when subject to the shear stress analogous to the bowing of a string. So in this way, you can do that. Now, if you look at the geometrical, 2t sine theta by 2 is equal to tau p capital L. And capital L is the, what is that? Now, it is the interdislocation distance or distance between two dislocations. So, what will to point where you can see that tau t equal to half gb square. And if you put that, and then you can understand what will be the radius of curvature. Now, dislocation, when we can understand the dislocation bowing process due to the force acting in the middle between two dislocation, then dislocation, middle of the dislocation, not two dislocation, one dislocation, and the line of the dislocation, then the bowing is occurring. Now, if two end, take AB are dislocation, and A end point and B end point are pinned by either solutes or dissipated or something like interstitials, and you are putting a force tau p on the dislocation line. And what is going to happen? It bows like B. Okay, in the figure B, if you can see that bows is there, and then you can again putting the force that looks like a bowing is going to extreme, and after that it looks like D cases. You can see that it's just going to very much totally it's going to a scenario where bowing is much more extreme cases due to the pressure is increased. And when it will do that, then sometimes it will just stretched and torn away apart, and now the new dislocation loop is created inside that the original dislocation you can find. So these actually known as per the metallurgist or material scientist Frank and Reed. So Frank Reed source of dislocation. So how it works? Now thumb dislocation during the process of recrystallization, it can pin or something like that. More dislocation are created during the plastic deformation also. So is a dislocation breeding mechanism what I discussed last 10-20 seconds. There we go. So that is the Frank Reed source mechanism. So in this way, due to plastic deformation, other phase transformation, thermal stress, due to thermal stress, multiplication of dislocation will occur or may occur. Now, here an experimental picture for silicon, the Frank Reed sources in the silicon. Here you can see the dislocation, how it is representing. That here is also the bow phenomena is there, but in the same, it's a continuous process. You can see discrete way it is happening, but it's a continuous process. That's why in the same picture you can see the different stages of Frank Reed source or Frank Reed source mechanism for dislocation multiplication. Now, let's take a case study to understand the dislocation much more clearly. So A case and B case, both are. One is the both dislocation in A cases are same direction, same half of extra plane or extra line of atoms. You can tell in the same half of the plane, the same side of that slip plane. Here you can say that in B cases just opposite. The one side of the slip plane is the extra line of atoms, and another side also slip plane also having one side of one line of atom, but they are apart from each other same, and the distance of two dislocation inter distance, or you can take the distance between two dislocation are same in both cases. Just two dislocation are opposite, and both are edge dislocation. So and we are considering two parallel edge dislocation lying in the same slip plane. They can either have the same sign if you look at the figure A, or they can have a opposite sign that will look at the figure B. When the dislocation are separated by large distance in the total elastic energy per unit length of the dislocation, both situation will be a GB alpha GB square alpha GB square. Okay. So when the dislocation figure are very close together, it can be considered approximately as a single dislocation with the Barger vector magnitude 2b. Then what is the elastic energy becoming alpha G 2b square. So which is the twice of the energy of the dislocation when they are separated by large distance. So now what we understand that if dislocation are placed very closely, then their elastic energy will be increased much higher even with respect to the when the dislocation are placed much higher or larger distance apart. So thus the dislocation will tend to repel each other when you just reduce their to reduce their total elastic energy. So the driving for the repulsion process is the reduction in the they want to reduction in the elastic energy. So that actually driving them to repulse when two dislocation are closely spread. Otherwise, what will happen? They are going to create a scenario where very large distance, so the energy will be elastic energy will be much less. Already you have seen from the case compared on the figure A and B, both cases. When dislocation are opposite sign are close, the effective magnitude will be 0, and that actually reduce the elasticity, and that actually reduce the scenario where the positive and negative velocity try to annihilate and come close and annihilate each other. So there will be a minimum energy that is 0. So that is the driving force for the attraction of two dislocation. Now, next question. Already we have discussed a part of this question last class, but here we are going to understand, or we are going to get the information regarding this question. Where can a dislocation line end? Dislocation line cannot end inside the crystal. Last class I told that, and we have understood also. Now it must end on a free surface of the crystal. That may be a surface, or that may be a crack, surface of the crack present inside the crystals. So ends on an internal surface or interface also, form a loop, closed loop. So I told that dislocation can close and form a loop, but dislocation cannot end abruptly inside the crystal and ends in particular node. There is a 3 dislocation can create a node, meet or 2 dislocation meet. That can occur, but then ends in node. So there is a 4 possibilities are there. 1, ends on a free surface of the crystal, ends on an internal surface or interface, or form a loop. It can and ends in a node. A node, what is node? The new term is node we encounter. That is, node is the intersection point of more than 2 dislocation, and the vectorial sum of the Barger vectors of the dislocation meeting at particular node is equal to 0. So now you can understand that dislocation line cannot end inside a crystal. And already I told last class also. Now we have to understand what will be the fate of the dislocation, where it will end. It must end on a free surface of the crystal, ends on an internal surface or interface, or it will form a loop, and it can be closed inside the crystal but cannot be ended. So ends in a particular node. Now we are coming across a new term immediately, that node. And what is node? Now where the 2 and more number of dislocation going to meet, and after meeting there, if you take the vector sum, Barger vectors of the all the dislocation who meeting at that point must be equal to 0. Then you can tell that is a node. So at that node, dislocation can end. Now dissociation of dislocation we are going to understand why it will occur and what is the phenomena, those things. So first, if you want to know why dislocation, dissociation occur, dislocation, repulsion and attraction we understood is driven by the reduction in the elastic energy after the phenomena. Attraction phenomena or repulsion, both are driven by the making scenario such a way so that there will be a reduction in elastic energy. Now, if you want to understand dissociation of a dislocation, then you have to understand how to minimize the dislocation presence and such a way that the energy of a system will be reduced. So dislocations dissociate to reduce their energy cost, means energy. So energy associated with them, they want to reduce that. So now it is clear to all of us that dislocation dissociate due to reduction of their energy cost. So now take a reaction. The two Barger vector divided into two B divided into BB to with a two dislocations. So again I am repeating, a dislocation having Barger vector 2B going to dissociate to become a two Barger vector. One will have B Barger vector, another will have same B Barger vector. Now, if you want to calculate the change in energy, then you can find the change in energy is GB square. This reaction then it will be favorable because if you reduce the energy cost associated with the dislocation from full dislocation to the partial dislocation or dissociated dislocation, whatever you like, you can represent or you can tell that, then what will happen? The dislocation reaction will be favorable. Now, if you want to correlate with the dislocation with the different closed back system, and here I am going to discuss about the cubic closed backing crystals, where the dislocation, how they are working and how will be their association with the slip system. So suppose consider a slip system of 110 direction, that is a closed back direction for the FCC crystal, and the family of 111 plane, that is the closed back plane family for the FCC crystals. So a perfect dislocation can split into a partial to reduce the elastic energy, because always you should remember that whatever the movement of dislocation or dissociation of dislocation, always energy driven, means the process should end up with a reduction in associated elastic energy or associated strain energy. So the dissociation of a dislocation into a partial leaves a stacking fault. And that is the very common phenomenon. Now you have to understand what is stacking fault. In order to understand what is stacking fault, you have to understand what is stacking. Stacking is logical and very proper arrangement or perfect arrangement of different layer of atoms inside a crystalline material. And if something is wrong, some layer of atom is missing or some layer of atom is coming not following the rule as per the bulk of that particular crystalline material is created, then you can tell that that is a stacking fault between the two partials. That's why the two partials also, you must remember, contain or include the stacking faults, or you can tell that the stacking fault is going to be occurred between two partials on a particular slip plane. Now, two partials repel each other and want to be as far as possible, which leads to a larger faulted area with an increase in energy, thus depending on the stacking fault energy. And there exists an equilibrium separation between the partial. I told that force acting on the dislocation is equal to the force, frictional force from the lattice is providing to, or crystalline provide to the dislocation. So resistive force is there. So that also needs a balancing act. And why two partial will repel each other? That you have to understand. Because two partial are having same direction of Barger vector. So they do not want to close, because then only they can, if they go as far as possible, so that they can minimize the energy. Now, they are not separating to infinity distance? Because there is a frictional force also there. So that corresponding optimality, or you can tell that corresponding equilibrium condition or equilibrium separation between the partials, are essential criteria for identifying the width or area of stacking fault. Now, the Shockley partial in a closed packed system or FCC crystal has a Barger vector of 1/6 or in the third bracket 211 type, which connect B side to C side and vice versa. So, for a closed pack ABC stacking, for a closed pack FCC crystal, you should remember the stacking, proper stacking is ABC, ABC. But you are going to get, if such a partial is there, then maybe ABC, AB, AB, ABC, ABC, AB, AB, such a way. So for a pure edge dislocation in closed packed crystal, for a pure dislocation in closed packed crystals, Barger vector which connect B side to C side and vice versa. For a pure edge dislocation in closed packed crystal, the extra half plane consists of two atomic planes. The partial consists of one extra atomic plane each, and the Barger vector of the partial is not perpendicular to the dislocation line. These things are very important statement one should remember, and that can be understood just by a simple geometrical drawing. You can draw yourself, and then it's a very obvious thing that you can see that partial cannot, the Barger vector of partial is not perpendicular to the dislocation line, although their full dislocation are edge dislocation. So a perfect dislocation, edge dislocation, and in Shockley partial, if you want to see the geometrical representation and the reaction I have given here, you can see that. And why the dissociation occur? Already I told that it's occurred due to the meaning to reduce the or minimize the elastic energy, and the perfect dislocation split into two dislocations partials when there is a minimization or reduction in the elastic energy. And there are also slip system, and that slip system also directly correlated with the Barger vector. You can see slip system. Regarding slip system discussion, already we understood. This picture help you to understand how Barger vector is aligned with a different slip system. Simply that part I have given through this thing. Okay, and you can also find the parallel planes. What are the parallel planes? This one. So for the FCC crystal structure. Thank you for today lecture.